So, welcome to the lecture on what is essentially how to get a spacecraft from the Earth to Mars, part of the College Novel Lecture Series for our college novel this year, which is The Martian. Really, this is, the technical term for this is orbital mechanics, right? But you don't have to worry about that. Well, the real big thing is, how do we get stuff from the Earth to Mars? Right, and it really requires those three guys: Johannes Kepler, Isaac Newton, and Walter Hohmann. The first two you probably have heard of, right? Because you probably got them someplace in like 5th grade science, and then again in high school science. The last guy you probably don't know much about. And so we'll spend a bit of time talking about, why Walter Hohmann is so important. But they're all kind of remarkable in their own way, really. The big thing you have to realize is that for your generation who grew up with Star Wars and Star Trek and things zipping around, in CGI land in the movies, or anime or anything else that you're watching, that's not real. Not at all. We are governed absolutely by laws of physics and the limitations of our technology. We have hydrazine thrusters, we have ion thrusters. We do not have warp-capable stuff. We don't have TIE fighters that burn whatever the fuel is that they burn, which allows them to do and act funky and behave like aircraft in an atmosphere. Doesn't work that way. So we have way more limitations, and so we have to work within those limitations to be able to get stuff from Earth to Mars anytime we do this. The first guy that's important is Johannes Kepler. I know everybody gets taught about Isaac Newton first. Kepler came first. Kepler was 60 years before Newton. So just to keep everything in perspective, that first bullet that I have up there is kind of important. It gives you an indication and a really readable explanation of exactly what Tycho Brahe and Johannes Kepler did and how important they were to understanding our solar system and really our universe. It is a very readable book. And Kitty Ferguson does an amazing job while doing it and while writing it. And the nice part is it's available through the Sussex County Library System. So if you ask, not the college library, but the actual Sussex County Library System, if you go into their catalog, it's right there. The other thing which should amaze some of you is that this is just over 400 years ago, and the fact that Kitty Ferguson could go back and get primary source materials which have still survived to this day from a little over 400 years ago, to be able to piece together this story is kind of impressive all by itself. Just to give you an idea, again, for those of you who are used to instant gratification from the internet and all your electronic devices, it took 2 years. Kepler started talking to Tycho in 1597. It was only in 1599 that Kepler actually got a job with Tycho and moved in. Tycho owned his own island, or actually was given his own island. For the work that he was doing, and Kepler moved in as part of his staff. All right, well, 2 years. I mean, they were handwriting actual letters, putting it in the mail, and letting people carry them from place to place. 2 years after Kepler joined Tycho and was kind of consigned to being a human calculator, Tycho died. 1601, Tycho died of basically gluttony at that time. And that left Kepler up a creek without a paddle because he was trying to use, in his spare time, Tycho's observational data to come up with his own Kepler's own view of how the universe worked or how the solar system worked. It's worth noting that the observations Tycho was making were not with a telescope. This is an actual plate out of his book, out of one of Tycho's books, and it's called an observational quadrant. Right, that stick which is in the center, sort of at an angle, that's the thing you sighted along, and then you pivoted this entire thing, and so you got angle and azimuth for any observational object that you were looking at, and you could track it and continually make observations during an evening and track it across the sky. So there was no telescope involved here. To give you an idea of how accurate they were, though, they were good to 1 minute of arc, which is really, really good. Take a dime, sort of turn it on edge and put it in a far corner of the room, and that's how good they were. Since Tycho died, and Kepler needed or wanted to continue, his search for how things moved in the solar system, he kind of appropriated some of the observational records and continued to work on the problem. He got employment as casting horoscopes and as a private tutor, all those kind of funky things that you had to do at that time. And he didn't come up with his final laws of planetary motion until 1609. This is 8 years later. Right? This is 8 years of hard graft and mental exhaustion, right, to get him to this point. For the math people in the, who might be listening, this is 8 years of work not using anything but geometry. If that statement causes you to break out in hives, that's a good thing. Think about, what Tycho did, what Kepler did, in 8 years of slogging through all of this data. If we use modern computational methods, a computer and calculus today, we can do the same thing in about a day and a half, if we really, really had to. And we had the right software. He was doing this all by hand. That's an actual book plate. That book is housed at the University of Edinburgh in Scotland, and I was fortunate enough to get to see the exhibit. That is what could be termed as the first centerfold. You needed a larger diagram, so you had someone hand draw the very large diagram. You then folded it up, and you had an extra piece. If you take a look at where the diagram sort of attaches into the book, you notice that there's an extra piece of the vellum or parchment, which is sticking out, and it got bound right into the book. And so when they got to that piece of the book, you could unfold this thing and get to see all of the diagram in its glory, which is kind of impressive, really. Kepler's laws, you probably heard Kepler's laws. Kepler is the first one to say that, he broke with the, past tradition, and he said, we do not move in circles. There are no great spheres. It is not the, crystal spheres of the heavens. This thing, the planets move around the sun in an ellipse, and the sun is at one of the foci, of the ellipse. Each planet also moves so that it traces out equal areas and equal times. So that means that going from A to B takes the same amount of time as going from C to D on that diagram, and the area encompassed by A to the sun to B is the same as the area from C to the sun to D. That's all that means. And then, of course, there's Kepler's actual book with the page open to his laws, those 3 laws. You can actually see them enumerated. They're on the left-hand side. Right, 1, 2, 3. He actually came up with many more. Some of them are related really to astrology. It's only the first 3 that have any scientific meaning. Kepler was a very interesting dude, really. Kepler's third law is just over 400 years old, and we use it every single day. If you are doing astronomy, if you work for NASA, if you are searching for exoplanets, if you are even an amateur astronomer, you use this thing virtually every single day. It turns out that the period of time to orbit around an object, squared, divided by the orbit's semimajor axis cubed is equal to a constant. That's at t squared over a cubed. All right, so think about this. If you start at A on the diagram and the amount of time it takes to go from A to D to B to C to A, that is the period of the orbit. The semimajor axis is the center of the orbit to the outside along the long axis of this thing. Now, it turns out a lot of the planets like Earth, we're nearly circular. Right, so the radius and the semimajor axis are almost exactly the same at this juncture, right? So all that's cool. Right? And that constant, if we couple Kepler's laws with Isaac Newton, which is 60 years later, that constant is related to the mass of the thing that you're orbiting around. Right? So if you were Galileo and you knew Kepler's third law, right, and you knew if Galileo was alive during Isaac Newton, right, he could make the observation of the moons of Jupiter, and knowing that and figuring out the distance, from the moon, to the center of Jupiter, that would be your a cubed, and if you measured the amount of time it took to get from a point back to that basically same point, observationally, that is your period. You could figure out what the mass of Jupiter is. We use this for exoplanets now. We can figure out the amount of time it takes for an exoplanet to go around its star. And we can measure the separation between those two using the Hubble Space Telescope and the Kepler Space Telescope. That will give you your a cubed. That gives you the mass of the star. Doing some spectral observation of that star, it also tells you what kind of star it is and all kinds of other things. That's really very cool. It will also tell you whether or not that planet is in what we call the Goldilocks zone, which is where we are, right, which could mean that it might have life, carbon-based life form, on the planet. So this is, Kepler's third law, even though it's 400 and something years old, is still very, very important. Now we get to Isaac Newton, and of course, it's the apocryphal story. Which allows us to explain what gravity does, and how it interacts. It doesn't tell us what it is. That took Albert Einstein to actually explain what gravity is physically. Newton gave us a formula. He gave us a way to calculate everything, which was really important because, honestly, Isaac Newton was one of the people who said, if you can't touch it, taste it, feel it, smell it, and experiment on it, it's not real. They were casting the, quote, occult, unquote, out of science. His explanation for gravity was action at a distance. There's no line, there's no string between us and, say, the moon or something else that makes things happen. So there was this spooky force that was doing something. The only reason that people didn't dismiss it out of hand is because A, it was Isaac Newton, and B, the calculation worked and worked so well and explained all of the motion except for Mercury. That required Einstein. The reason that we get the apple whacking him in the head apocryphal story really comes from John Conduit. Newton, not only was he a professor at Cambridge, but he was also in charge of the Royal Mint. As a point of just interest, if you look at the edge of your coins, if you pick up a a quarter. There are ridges on the edges of the coins. Newton is the one who invented the idea of putting the ridges on the edges of the coins. That prevented what we call coin clipping. Right, when coins were made out of a pure metal, people would just shave a little bit off the edges, and if you shaved enough off, a little bit off enough coins, right, you actually got extra money. But then the coin was not worth what it said it was worth because it was a little light. So putting the ridges on the edges of coins prevented this practice. Conduit was Newton's assistant, and of course, Newton was off in Lincolnshire in England. He wasn't at Cambridge anymore because the plague had hit again, and being rich and privileged, he beat feet and out of Cambridge, and he was waiting for the plague to pass, kill off all the peasantry, and so that he could just get back to doing what he wanted to do, which was be a professor at Cambridge. And so this is how John Conduit explains it. 1666, he, meaning Newton, retired from Cambridge to his mother in Lincolnshire. And while he was musing in a garden, it came into his thought that the power of gravity, which brought an apple from a tree to the ground, there's the apple whacking him in the head part, was not limited to a certain distance from the earth, but that this power must extend much further than was usually thought. Why not as high as the moon, he thought to himself, and that if so, that must influence her motion and perhaps retain her in her orbit, whereupon he fell a calculating what would be the effect of that superposition. Yeah, really bad run-on sentences. If you are interested, I do give you the link there or the reference there. It's Keysing's book, The History of Newton's Apple Tree, and it actually is quite fascinating reading. Notice though, it is 60 some odd years after Kepler came up with his laws. Right, so Kepler was working from actual experimental data, and he came up with his explanation for how things moved. Newton now is just working from one single object and doing some funky formulas, which look like that. And he's trying to generalize gravity. And so he says that the force between any two objects is equal to a constant. That's a big G. The product of their masses divided by their separation squared. And gravity is always attractive. That constant in front turns out to be a really small number. That's why your computer doesn't just suddenly fly across the room and attach to your chest, or you don't stick to whatever it is. I mean, you need a really, really big mass to make that force measurable. If you take that formula of Newton's, however, and you go ahead and solve it mathematically, turns out you get exactly the solutions that Kepler proposed. Right? The solution is the form of the equation of an ellipse. You do get equal areas and equal times. It's called conservation of angular momentum. It's also called a cyclic variable. It is the formal term for it in physics. And last but not least, you can manipulate the solution to the problem and prove that t squared over a cubed is equal to a constant value, which reflects just the mass of the object about which you are orbiting, right, at any given time. Could be the sun, could be a planet, just whatever it is you're orbiting around. Now, last but not least, the guy you probably not heard of, Walter Hohmann. That is not a typo. 1925, Walter Hohmann was a civil engineer in Dresden, Germany. And he came up with the idea that there was a orbit or a method to be able to get from one planet to another planet, or one orbit to another orbit, that would require the least amount of fuel. And what he then did was he went through and he did the calculation and proved it. Now that's quite impressive, because go back to those first two words, in 1925. In 1925, we had not had a rocket leave the planet yet. Nothing had even gotten out of the atmosphere. We hadn't had anything orbit the planet yet. Most of the rockets that were being created in Germany at the time, because they had amateur rocket societies all over the place, they would go out, they would build their rockets on the week during the week in the basement, and then on weekends they would take over, airports, and start launching rockets into the air, and stuff would blow up on the tarmac and get halfway in the air and explode and do all kinds of stuff. But that's as far as we had gotten. And this man had the vision to be able to see that we were going to get out there someday. And not only were we going to get out there, but we wanted to be able to go places once we got out there. Different planets, or even outside our own solar system. And so he came up with the idea to do that calculation. It's quite impressive, really. You may remember I said he was a civil engineer in Dresden in Germany. 1925, we were on the verge of the Second World War. And so Walter Hohmann, being the chief civil engineer in Dresden, Germany, was killed during the Allied firebombing of that city toward the end of the Second World War. Saved people in the city, and so we did not have the benefit of his brilliance, for too long. That's what a Hohmann transfer looks like. That center dot is the sun. The inner circle is the Earth's orbit. The outer circle is Mars's orbit. And that gold circle, the thing which is labeled transfer orbit, that is the Hohmann transfer, elliptical transfer orbit, to go from one to the other. Now, you would like Mars to be as close as possible to the Earth's orbit, so that transfer orbit has to be as small as possible. That means the time of transfer is as short as possible. Right? There is one problem with this diagram. It oversimplifies it. Right? It makes it look like, anybody could do that. Just send it out there. Right? You have to remember that everything in this diagram is actually moving. The Earth is moving, Mars is moving, they're moving at different rates, and then you're going to put a satellite in motion around this. All right, so now to give you an idea, if you just take a look at that diagram, top of the screen, the inner circle is the Earth, the outer circle is Mars, and the little winged thingy is the satellite. Notice that if you launch the satellite at the wrong time from where Mars is in its orbit, you miss Mars. And you never catch up. You will never make rendezvous. So you have to figure out how long it's going to take that satellite to get from the launch point at the Earth to where Mars is going to be. And then you have to calculate backwards to figure out where Mars is now. And then that determines your launch date. Not only that, but Mars is only close to the planet Earth every 26 months, roughly. So you've got this launch window that we are looking at. Now, to give you an idea, this is an image of being close to us, happens every 26 months or so, and the launch window is only open for 1 month, so between 25 months and 26 months, you have a launch window. So if you are prepping a mission to Mars, you've got 2 years and a month to get it ready to go and get it on top of the bird, or you've missed your opportunity and you're going to have to wait another 2 years and 2 months, to be able to get it to launch, which is a long time to hang around. And this isn't even taking into account how long it takes to actually get there. This is just when it's possible to do the launch. So you've only got, once every 26 months to do this. This is why just recently we've had a spate of launches. You had, I think it was Japan and somebody else and the US have all launched stuff for Mars, all within like a 3-week window. Well, that's your open launch window to be able to get to Mars for a minimum energy expenditure. Minimum energy expenditure is really important because the rockets require fuel. Fuel takes up space to be able to get where you want to go. Anything extra is where you can put all the sciencey stuff. And so if minimum energy means minimum fuel, more science. If you need more energy, that means less science. So that's why we want a Hohmann launch window for this thing. If you then use Kepler's law, Kepler's third law, and calculate the time it takes, the period, to use that Hohmann launch window to be able to, or Hohmann elliptical transfer, to get to Mars, and then cut the period in half because you're only going half the orbit. It takes about 259 days to get to Mars. That's pretty much a year. And now you understand why this decision in the book to go back and rescue him was such a big deal, because they were already on the way home. So now we're talking pretty much a year to get home. And then they can't stop. They're going to have to immediately turn right around and go back for another year just to get him. And then once they've got him, now they're going to take another year to get home. So this is 3 years of your life that you're sinking into this just when you make the decision to go rescue him. You have to know whether or not you got enough food, you got enough fuel, all the systems are operating perfectly, because you're going to do a gravity assist and slingshot around the Earth probably and go back to Mars. They may be able to resupply you, they may not. And you have to have everything you need. Not to mention the fact that the guy on the planet has got to be able to survive basically for 2 more years until they get there. So this, the angst and the tension in the book over that part, over them making the decision whether or not they are going to decide to go back to get him, once you know the science involved, is real. And it's really, really palpable, because you would hope that you would make that same decision and you make that right decision to go back and save the guy, but it's really going to be difficult. It's going to be difficult for him to survive that long, and it's going to be difficult for you to basically be stuck in this can, going out. Coming home knowing you can't stay home and you just got to keep right on trucking and then go right back out again, and spend another year to get there and then another year to come back on the whole thing. So I hope it was informative. I hope I didn't bore you to tears. And I hope this gives you a little bit better knowledge of the science that goes into or went into writing our college novel for this year. If you are interested in a little extra resources, I've got some basics of spaceflight. That's very readable. There is some math in it, but you can just skip over the math and the explanation will be good enough. If you are a hardcore math person, the second link, which is orbital mechanics, is probably more interesting to you because they're going to actually do a full-on calculation, as well as show you all of the math. And then that last one, we have been talking about Hohmann transfers. And that's the minimum energy transfer. There are patched conic sections, which is how we got to the moon with Apollo and a couple other things. And there is a new way to be able to get to Mars, which is called ballistic capture. And